What's up, YouTube? I'm coming at you today with a cheaper way to do autonomous precision navigation with your farm robots. Now, I've built a lot of farm robots over the years. We've got drones that fly and use AI to spray weeds. We've got mowers. We've got a weeder that uses Fresnel lenses to actually burn weeds. But what they mostly have in common is they use GPS and specifically GPS with base station correction to do navigation. That's what you need to get precision navigation when you're working your way over a field or a lawn or whatever it may be. The trouble is this Tier 3 GPS plus Cube Orange plus the telemetry to get it to talk to the base station is currently running about $800 online. That's a ton of money for smallholding farmers to put into robotics projects. So I want to use something else today called VSLAM, Visual Simultaneous Location and Mapping. Now, VSLAM is just a way of figuring out how your camera is moving through space and where you are relative to where you used to be. It is usually computationally expensive, a lot of CPU, a lot of GPU, a lot of power, and it could push the cost of all of the compute on here up into the hundreds of dollars, so comparative to what you see over here with this GPS. I have implemented call it VSLAM Lite, a really simplified version of VSLAM, but it nonetheless works for farm robots. We are using the simplification that farm robots typically travel in a grid pattern. So think of mowing your lawn back and forth, or flying over a field looking for weeds, or working down and back in a garden along garden rows and weeding. What you have in common is you're going down and back over and over. So with those simplifications, we're able to reduce the CPU and GPU loads significantly so that we can actually fit on this guy right here. This is a Raspberry Pi 5 with 2 gigs of memory, and this is a camera over here. Total cost is about $80. That is 10 times less than what you see over here. So call this VSLAM Lite for cheapo farm robots. After the break, I will show you how this code works and how to put together a little prototype so that you too can get cheap precision navigation on your robots.
Flying over a field or navigating a garden isn't quite like being, inside or in a forest. There's not a lot of vertical structures in front of you that you can use as reference points. The most distinct features are probably the plants on the ground near you.
Let's say that you want to walk a grid pattern over this entire field. There's not a lot of landmarks out here. That's why GPS is useful. But one technique that a person could use is walk in a straight line all the way to the end of the field and note any unique plants. This guy right here is a cherry tree, something that you're not going to find a whole lot of out here. And so when you see this, you can say to yourself, oh yeah, that cherry tree's on my right side. So I will walk in a straight line all the way down to that end, and when I turn 180 degrees and come back, I'll make sure that I see that same cherry tree and keep him again to my right side. That way, I know that this path is parallel to the previous. And if I have enough of those landmarks walking all the way down and back, and then continuing on to the next line, I can actually make sure that I cover every square inch of this field without GPS.
Full VSLAM does a lot. Camera position, 3D depth estimation, figure out your location in space, distance traveled, closed loops. We've simplified that quite a bit. Our camera is fixed and it's looking at the ground, and we know that our pattern is going to be back and forth in a grid. So let's simplify the code to the minimum we have to do to get this thing running. First thing is we need to figure out how far we've gone, and calculating distance is not that difficult. We take photos all along while we're operating, and we can compare one frame to the next to see how far we've traveled. What we actually do is we overlay features onto the photos. You can see those overlaid features on these photos here, and then we compare how far those features have gone. And this is the code that actually makes that feature matching and calculation happen. And then here we can actually see this thing operating. I put a simplified little track, it's just a piece of tape, in my office so that I could see this thing moving along a line and then turning around and moving along it again in the second row. So you'll also notice that this thing is stopping, and that is because I was getting blurry photos if I took photos while it was running. I need a better camera mount and a global shutter camera in the next version of this. But for now, to avoid blurry photos, we just pause every so often to take the photos. So that's it. We can drive in a straight line and we can figure out how far we've gone, in this case 30 inches or something like that. Second thing we have to be able to do is turn around. And again, we do the frame to frame comparison. So between each frame now, rather than distance, we're calculating the angular change. And here is the code that makes that happen. And Here is the robot actually running. So you'll notice that it turns 90 degrees, drives forward a little bit, and then turns again. And the reason for that driving forward after 90 degrees is, of course, to get us lined up with our next row. If we just turned 180 degrees and came back, we would be covering the same ground. It's not what we want. So turn 90 degrees, drive forward, turn 90 degrees again. Now that we're into our new row, our last task is before us, which is making sure that this row parallels the last row. And to do that, think about the previous row. On the left side of the images, we saw that there was a piece of tape. Now that we've turned around, we see that same piece of tape on the left side of the image, but it's rotated 180 degrees. So what we can do is take our photo, take the left side of that photo, rotate it 180 degrees, and compare it to the previous row. If they line up perfectly, then we are parallel to our previous row, and that's what we want. If it's pushed a little to the left or to the right, we know that we have a phase correction error. We need to jog our robot to the left or to the right to stay parallel to the previous row. Now, we don't actually just compare to a single image in the last row. We compare to the 3 or 5 most likely candidates in the previous row, just in case we didn't travel quite as far as we thought we had. And so doing this, we are able to decide, hey, which one of these matches up best, and should we move to the left or to the right? And here is an example of that photo, comparing left and right, and here is the thing actually operating. So you see it's moving down the second row, and at first it says, yep, I am in line with what I want to be, so I can move directly forward. And then it says, oh wait, I need to jog to the left. And the jog script is just turn a little bit, drive forward, unturn, and then back up. So we jog ourselves to the left maybe a couple centimeters, an inch, something like that. And then we drive forward again and take another photo. So we can continually do this, compare where we are in the row to where we were in the previous row, and decide if we're online or we need to go left or right. And that's how we make sure that we parallel our rows. That's the secret to VSLAM Lite. We have way less CPU and GPU as a result, and we've greatly simplified the problem so we can cheap out on hardware and software and still have a farm robot that works.
Assembling this thing is like falling off a log. It's one of the easiest robots that I've had on this channel. All of these information on how to build this, the files, the source code for how to create the files, the code that you actually run on the Raspberry Pi, as well as the wiring diagram and the list of parts are at the GitHub linked below. So when you actually go to build this, you are going to first off 3D print the files. So you've got to print 2 back wheels, 2 front wheels, 2 of these brackets that hold the front wheel, 1 body, that's this big square piece, it's all one piece, and then 1 of these camera holders right here. So get those all printed up, and then we're going to do some assembly. The first thing you have is you've got these ball bearings. You see right here at the end of this axle is a ball bearing, and the ball bearings are what make these front wheels run. So you're actually going to fit the ball bearings into the top and into the bottom of every one of these front wheels. And then you're going to take your front tire and you're going to put a ball bearing right here and a ball bearing right here, and then run an axle through there. And the axle part is also linked below. Now I went ahead and I drilled a couple holes at the end of that axle there. And the reason is this is a tiny, tiny wire here, and you can fit that wire through, think of it like a linch pin. You can fit it through the hole in your axle. So the next thing you're gonna do is start the assembly process here. So pull this back out. You're going to fit your front bracket over the front wheel, and then push your front axle through there like so. Now you see it sticks out a little bit on each side. And I have, like I said, one of these little tiny wires that will fit right in here. I can just bend it, and then I do the same thing on the other side. There we go. Bend it over, and now you've got an axle that's been captured in there, and this wheel can spin nice and free. So next thing, you take your assembled axle here. You have to cut it to the right length so that it bottoms out, or nearly bottoms out. And this little piece of plastic right here butts up against your ball bearing right there. And then I went ahead and I drilled a little tiny hole and put what I call a set screw on here. This screw is going to pinch against that piece of metal axle that you have in there, and it keeps this thing from wanting to move off that way in operation. You can't always depend on there being enough weight on there to keep it in place. So screw that set screw in place. Repeat that process on the other side over here. And now you have two front wheels. They can rotate and spin, and you're all done. So it's very simple front wheels. Now for the back wheels, these actually have a D axle, a D-shaped axle right in the middle of them. And they are the perfect size to fit over the motors that are linked down below. So you need to figure out which side is slightly flat. I went ahead and drew a line on there so that I would know. You take your frame here, put your motor just right in this little housing right here, and you can see that there are screws that actually screw into the motor, and all you have sticking out is the D axle. This is just a direct drive. It's like the simplest design I could make because it's just a prototype, so we don't want anything fancy. So take your wheel here and set it so that the flat side of the axle matches up with the flat side of the D cut out in the middle of your axle. That's the body assembly of this thing. You now have front wheels and back wheels, and it's time to put all the other stuff in. Not a whole lot to it. So first off is the power system. I decided to use wall power. In the future, I really should use 12-volt battery power. But for now, this wall power, it's 120 volt here where I live, it comes in here and it converts using this USB. This is the official Raspberry Pi USB. It's just 5-volt power, but it's pretty high wattage and it keeps this thing running. I believe you could run this off of the GPIO pins, but from what I read, it was a bit of a hassle. You got to get a lot of power to those GPIO pins. I thought it was just easier to do this for now. And then this thing here is just a wall power to 12-volt conversion. So you're going to take your the power coming out of here, the 12-volt, and just run it straight over to your electronic speed controller mounted right here. Make sure you get the plus and the minus set correctly. And then the outputs of this electronic speed controller here and here are just going to go to your motors. So you got to solder these wires onto the back of the motor. This is just 18 gauge solid copper wire with a little red and white. So you got power coming into your ESC and the voltage is going out. And then the last thing is you've got to hook up your Raspberry Pi to this electronic speed controller. The only things that you're controlling are the pulse width modulation, PWM, and the direction for each of these motors. So in other words, how fast and which direction should it be going in. So a total of 4 control pins and then a single ground pin. And here is that wiring diagram. Here's what it looks like in operation. You can see there's a bunch of wires coming out of the GPIO pins of your Raspberry Pi, and they come over here and they plug into this little header of the electronic speed controller right here. And that's really all the, oh, I'm sorry, one last thing. You've got to take the camera output from your Raspberry Pi 5 and mount this little camera bracket right here. I just took a couple screws, screwed it into the frame right here, and then there's a little hole right there for your camera to see, and this thing centers it more or less in this square right here. Now, in the future, I actually want to have worm gears that move a laser along this, like you see back here. So this guy has a laser which will be used to burn weeds, and there's actually worm gears around here as well as some lights that light this up so you get better lighting and identification. And this prototype could be pretty easily modified if you just took the Python code for this body and threw on stuff like that. Or you could try to put a mount for a motor so that you can do mowing if that's what you think you want to do. This thing could be modified fairly easily for any of those sorts of needs. But that's how you put this whole thing together.
Once you have this all put together, you're going to want to put the code on the Raspberry Pi. You just grab one file out of the GitHub. This is that file. And then drop it on anywhere on the Raspberry Pi in your home directory. And at the top of that file are the set of instructions that you need to install all of the libraries. So you run those couple instructions. It'll install all the dependencies that this script needs. And then the actual way to run this thing is just a single command. You see that command here. There's 2 parameters. The first one is how far you want it to go in pixels. And the second one is how many rows you want it to do.
I've started using Pi Connect. So from my laptop, I use Pi Connect to connect into this thing, and I can, it's as if I were connected to this with my keyboard, video, mouse, and I can run whatever I want on there. I actually did most of the development on the Pi 5 itself. Couple last thoughts. This is obviously a prototype. It's not super rugged, resilient. It does need to be improved, but you can modify as you need. Second, the actual code that does the navigation should be improved. We need less blurry camera images, so a better camera mount and a global shutter camera. Probably better algorithms to do the phase matching, so that we know if we need to move left or right. And then of course, LiDAR, so that this thing will run properly is probably a good choice, so that it can do obstacle avoidance. But you know, it's a pretty solid start, and it's 10 times less than what I had been spending on precision navigation. So definitely worth a look. Please take this, it's all open source, modify it, make it better, and please put it back out there so that other people can use it.
Let me know what you think in the comments, and don't forget to like and subscribe for more unique and useful do-it-yourself builds.